Zaczynać. I'll give this talk in English because I'm recording it. So today I'm gonna take you for a fast tour of my favorite language. Who am I? Let's start with this. So I'm Adrian Ostrowski. I work at IPAM. I was raised in a farm, so I had lots to do with crop fields. Now I work in a kind of different field, software development field. I'm a C++ programmer for 6 years now. When you talk about the East Const and West Const debate, I'm the West Const propagator because I think it's more standard. I like to write high quality code. I'm a lifelong learner, which in C++ is kind of needed because the language constantly evolves and there's lots to learn. I like music. I was organizing some concerts in Gdańsk, like Machine Supremacy a few years ago. And I like to play games, lately mainly Rocket League. Okay, so this is what we will talk about today. There are some bits about history of C++. There is a section about modern C++, and I will take you through the features of the language. So let's start with a pinch of history. Probably all of you know this guy. Bjarne started the language. Let's talk about how it started. So he was writing a doctor's thesis in Simula, which was a language giving him high-level abstractions, but they came at a cost, and the cost was too much for him. So he decided to rewrite it to another language, a one which gave him lots of performance. It was BCPL, a language from '67. And it turned out all the abstractions were gone. So he didn't like it. And he promised to himself that if he will be doing something similar in the future, he would need to have better tools, even if it meant he will create ones. So when he was doing a job when he was working at Bell Labs, he had this assignment about Unix kernel and concurrency, and decided that he noticed that he has the same situation, so decided to create his own language. That's how C++ was born. He decided to base it on another language, which was also from Bell Labs, the C language. And because of the portability and the performance that it offered. So the guys at Bell Labs really liked doing new languages. They created B, C, C++, and even a few more. And Bjarne, since the beginning of the language, had the same philosophy in mind that C++ has today. Namely, that it should be as close to bare metal as it's possible, and that you shouldn't pay for features that you don't use. So this way, the language could offer high-level abstractions, coming at hopefully zero cost. Sometimes it turns out that the cost is even negative. So 6 years after Bjarne started working on C++, he released the C++ programming language book, which is the first reference book of C++. Then he further developed the language. Then the 90s came. Do you know this guy? Do you know who it is? Who he is? Anyone?
Stepanov.
Yes, exactly. It's Stepanov. Alexei. So he invented DSTL. And templates were introduced like in '91. I think in '92 he already had some implementation of DSTL, but he didn't want to write a paper to bring it into the standard, at least initially. And Andrew Koenig, who was his colleague from work, they had a debate about if he should bring the language or not, bring DSTL to the language or not. So Stepanov thought that probably it won't get into the language anyway if he proposed it, and Koenig agreed. He said that yeah, DSTL won't get into the language if you don't propose it. So this is a great example why you should write standards if you find something missing in C++. Okay, but let's move forward. So we have the 90s were an era of desktop applications, object-oriented programming, and C++ really shined in those years. It was used everywhere, but simultaneously to C++, other languages were developed, like Java or C#. And so those are the coffee-based languages. And with the increase of power of the desktop PCs, it turned out that the gain that you had, the performance advantage of C++ over this language, wasn't that important, because the other languages could do everything pretty well, and still you could write code easier in them because they weren't as complex. So the 2000s were really a bad time for C++, and it would probably become the new COBOL, if not for a few things that happened. One of those is the rise of mobile platforms. And it turned out that for mobile platforms, a different set of priorities is in place. So you all know that it isn't about pure performance on mobile. You also probably care about battery life. So performance per watt is really important here. And C++ really gave it to the programmers. Also, the memory consumption of C++ programs is usually lower than those of, let's say, managed languages. And another platform that C++ is really good on is the cloud. This is because of the scale of the cloud. So if you are writing code, even with a small performance benefit of C++ compared to other languages, if you have 10,000 of machines or even more, this really adds up. So if you take Facebook, for example, you could understand why their backend is written in C++. It really gives them, each millisecond saved really gives them millions of dollars. And C++ is still strong on other platforms as well. So on the left side, you have a talk from CPPCon from Jason Turner, who was able to code a game using C++ 17, which was run on Commodore 64. I think this is pretty impressive. And he was able to play it fluently. And the other platform where C++ is good at is, let's say, NASA software in general. So space exploration software heavily relies on C++. If you talk about other places, you have all the fields where performance matters. Just pure performance, like for game development, you have many game engines written in C++ and high-frequency trading applications, when each microsecond can matter if you want to be faster than your competence. Also mission-critical systems like airplanes, operating systems, except for Linux, the automotive industry, blockchain applications, so Bitcoin, for example, is written in C++, and building blocks for AI and machine learning, like the TensorFlow framework, which is written in C++. If you look at the IEEE spectrum rating, it looks like the language really isn't dead. It's quite the opposite, actually. Probably because of the high-level abstractions it gives, the portability, the low-level access. It all sums up. Okay, so let's move to another topic. I would like to say a few words about modern C++. I'm not sure if you know what it is. So, do you think it's C++ 11, maybe 14, maybe 17? Perhaps it's whatever the newest standard currently is, and it's changing with years. So I have a different answer for you. Modern C++ is not about the standard, it's about the philosophy of coding. And if you look at C++ 11, it was heavily influenced by popular libraries and practices, like coming from Boost. So, who knows which year this book is from? You can guess.
2006.
It's older. It's even older than that. Any other guesses?
2000.
You're very close, but it's younger. So it's actually from 2001. So, as you can see, modern C++, which was born with this book by Alexandrescu, is not that young. And how is it different from the C++ that so many of us are or were used to? So the first main difference is that it gives you the RAI idiom. We will talk about it in a second. It also promotes the reuse of standard library components. And not only the standard library components, other libraries as well. It offers you many possibilities with templates and metaprogramming, which isn't that hard as it looks. And you can mix programming paradigms, a thing that actually other languages are implementing as well, since recent. Okay, so let's talk about RAI. So the acronym means Resource Acquisition is Initialization. And who has ever leaked a resource? Okay. Maybe you double-freed a resource. Yeah. Who hasn't, right? Maybe you had a hard time handling exceptions with releasing resource concerns. Probably too. So RAI is here to take the burden of that and to free you from all those troubles with low effort. So let's look at an example. This is a very simple smart pointer in just a few lines of code. It doesn't offer much functionality, but you can see that in the constructor it gets some allocated memory. In the destructor it will always automatically free the memory. And you won't get issues with double free because you have, it's not a copyable object. So you can see that the copy assignment operator and the copy constructor are deleted. And maybe another question: how many, who of you works in a company that has its own string implementation or had one in, yeah. And it isn't really in the spirit of modern C++, so you should reuse components or libraries if it's only possible. And you can do it by several means. One of them is generic programming. Another of them is policy-based design. I will show you a slide about it in a second. And you can also reuse whole libraries. Believe me, many string implementations are there on the market, open sourced, you can use them and probably save time writing your brand new another string. So policy-based design is a simple idea that you have a class which you can parameterize in compile time to change its behavior. If you look at the treasury that I've got here, you have this overflow policy, which is another class, and it has to have this check function, which will perform some logic in case you want to add some funds to your treasury. So let's see how a policy is written. I have this Robinhood policy here, and it has a check function implemented, just like require. And if so as you can see, you can do lots of stuff here, like save some money for later, and you can create a concrete treasury using a type alias, for example, or a type def. So just parameterizing the treasury with Robinhood policy, we get the Nottingham factory. Okay, so let's talk about reusing existing libraries. I have a few here. So the first one is Boost. If you don't know it, you really should. It's a must to know for every C++ programmer. Another one is very interesting. It's Upsale from Google. It was released a year or two ago, and it allows you to stay on top of things even if you're not able to use the latest C++ standards. So if you are using C++ 11, if you use Upsale, you can have features from C++ 17, like optional, variant, string view, and many others. Also some string helper functions. The next ones are EASTL, which is Electronic Arts version of the STL, containing many utilities. The next one is Bloomberg's BDE and BSL. They have also lots of interesting utilities, all written for performance. And the last one is Folly. It's a C++ library from Facebook. And you can, if none of those libraries has the component you want to use, you can now use your own library, with one that you found somewhere on the internet, using package managers like Conan. So Conan is actually quite an easy to use and powerful tool, and it plays nice with the current C++ state of things. So let's say you want to use a range v3 implementation from Eric Niebler. It's a great library which I will show you later. So you just put it in the requires section. You can specify some options also, and specify some generators like CMake, which is also de facto standard for the C++ language. Then you have the CMake lists. For those who know CMake, it's pretty simple to add Conan to your project generation. So you just include one CMake file generated by Conan, and then set up the targets using CMake. The targets approach is suggested for now because it's better than the old CMake variable and the variable style, because it scales much better. And you can just link the library using Conan package range v3. You don't need to specify into directories, it will be done automatically. And then run some simple commands, and you can start using your ranges library. Okay. Another thing that modern C++ is fond of are templates in metaprogramming. So you could write this code to compute a factorial. You need to have a template. The template calls itself with a different parameter using a recursion call. But if you find this a bit ugly, I have good news for you, because in C++ we also have context super functions. And it turns out that C++ actually goes into this direction. So instead of those three templates, you could just write this simple function, and it will compute the same in compile time and runtime. Since C++ 14, you could use loops and if statements. And another interesting feature for compile time programming is the static assert. So you could actually check the result of this function in compile time, and the build will break if you have a bug. So it's like a mechanism for writing unit tests for your C++ compile time code. And it really looks like we have more and more push for the compile time computations, and they get easier with each standard that comes up. Okay. Another thing from modern C++ is the ability to mix programming paradigms. So usually people think of C++ as the imperative language to write object-oriented code with lots of dynamic polymorphism, but it's not the whole story. And you could, for example, use the generic programming principle, and the STL is a great example of this. And there are several facilities in the language that allow you to write good generic code. So templates, the auto keyword, and the conscript functions that we already talked about. Another paradigm you could write in is the declarative style of programming, as opposed to the usual imperative style. So if you look at the example using the ranges v3 library, I think it's actually much more clear than what you usually see in C++, but still it's very powerful. So I'm creating a range here, taking the infinite stream of integers. It's a lazy evaluated stream. Then filtering it using a simple lambda. So we will have only the odd numbers. I'm removing the first one, and then taking the three next. So we have 3, 5, 7. Reversing their order, transforming them to a string, and accumulating. And this way we get the year that Rome was built, 753. And okay. Another paradigm that you could write in is the functional paradigm. So lambdas are a great example of it. So now functions are first-class citizens in C++. You can also write composing function of a simple lambda to compose other functions and return closures. And this is just a small sample of what's possible. And if we sum up this section, modern C++ usually results in safer, cleaner, faster to develop, and faster at runtime code. And it turns out it's a great match for the recent C++ standards. So let's talk about the evolution of the language. So I think we won't talk a lot about the past. I think every one of you knows it, and if you don't know it, you really didn't miss much. So let's start with C++11. One of the key features that was introduced in this standard are move semantics. And as you can see, we have a unique pointer here, which is an example of the RAII pattern, similar to our smart pointer, but much better. And using move semantics, you could pass ownership between several unique pointers. So there's only one responsible for freeing the resource. You can also use a shared pointer for this if you need, if you want to have shared ownership, and then only the last one that is deleted will delete the memory, the resource underneath. Move semantics are also good for performance, because instead of creating unnecessary copies, you can just move the resource. And it creates an R-value reference. So if you're interested in the topic, you should read about those. It's a similar concept to creating a temporary object, a new object. So another thing from C++11 are variadic templates. And they are a great tool to write compile time functions. They were used to implement, let's say, std tuple type, so a data structure that you could use to return multiple values from a function. They can also be used to implement your own make unique in C++11. This feature was added in C++14 actually. Another thing added in C++11 were initializer lists. So those are just lightweight lists of values, and they can be used to construct objects on the fly. If you remember how creating a map worked in C++98, you should first declare the map and then just add elements to it, which was quite inefficient. And here, with initializer lists, you can just add elements in place using in the same moment that you declare the map. And the syntax is also, I think, quite understandable. We already mentioned static asserts. You can use them, for example, to detect the platform. They can be a great tool if you are writing your own serialization. And they are a great help if you are implementing compile time functions, or even if you are using, even if you have to do some checks like for the template arguments. Another addition was the auto keyword. I guess all of you know this one. It allows much more than just to help lazy programmers. So it can be used to assign lambdas, for example. It can be used to eliminate unnecessary copies, because you will always get the kind of item that you want. And there is a case with the map iterator where you create a copy instead of just using the type of the iterator that you should. So speaking about map iterators, as you can see, it's much clearer to write just auto and then declare the iterator than specifying the whole type. So we said about lambdas. As you can see, you can have a few quirks with the lambda declaration. Lambdas are basically functions that you can evaluate whenever you want. So
The first line won't actually print hello world because it's not called using the call operator, but it's a full-blown lambda. The next middle example, as you can see, you have two lambdas. One is catching the parameter using a reference, and the other is creating a copy. If you want to mutate the state of the lambda, you have to add the mutable keyword because it's constant, because it's constant by default. And lambdas really play very well with the standard algorithm. So you don't need to create another function. You can just pass a lambda in place. And in this example, you have a function sorting the elements of a vector using their absolute values. Another small addition was the range-based for loops. It's a small addition, but it's very convenient, as it can save you from writing long iterator-based for loops. We also have concurrency facilities, which I won't discuss here in details, like thread, atomic, and mutex classes. And the mutex and locks also follow the RAI principle, so you shouldn't have much issues with deadlocks if you're using them. Another great addition was the chromo library. You can use it for simple benchmarks. And they are, so this is the example above. There are several types of clocks. You can use them for various things in times, and they are offering also quite nice compile time based conversions of the units. And since C++14, you can use literals with them, so it really gets more natural, as you can see in the last line of the example. We also have some new containers in C++11. So we have the hash containers, like an ordered map and an unordered set. We have the tuple that I mentioned already. And we have an array, which is a constant-sized array you can use in compile time. So let's quickly jump through C++14. And it added generic lambdas. So now you could write one lambda, and depending on how you use it, it can create a few concrete instances. So if you change the type in a vector, as you can see, from int to string, the lambda stays the same, and the same lambda can support both those cases, which saves you work. So let's talk about the more interesting stuff, C++17. One of the additions was fault expressions. And they are a great tool if you are writing if you are using variadic templates. Since now you don't need to use recursion for your calls, you can just use this ... syntax. And in this example, all arguments will get inserted in just one statement and multiplied. Another addition was const per if. So now you can have an if statement based on some compile time constraints. This is how you could write a Fibonacci function in older C++, like C++98. And this is how you can write it now. And I think it really resembles the runtime code. So this is actually based on a compile time parameter. You can even write a lambda which is returning two different types depending on the input parameter. Another addition to C++17 was initializers for if and switch statements. And as you can see, you can now lock a mutex in the if statement, and it will remain locked in the whole if and else statements. And then you could check. So first we have the initializer, and then we have the check. So we check if the vector isn't empty, and if it isn't, we can pop an element, after which we will release the mutex. And it also works with switch statements, as you can see. If you ever had to write a few sections of code using this, and you had this issue with naming things, because you wanted to reuse the same name, but it was already taken, so you created sections. You could now, and if you were doing it for if statements, you could now use this. It also plays nice with structured bindings and map iterators. So if you insert an element to a map, you get actually two values in a pair, an iterator and a Boolean value, which says if the insertion happened or not, created a new element or not. And then you can check if the element was actually created in a map or it was already there. Another feature from C++ 17 is the variant type. This is types if union basically. So I guess you know unions and the issues with them. You could never know what type is in a union. You couldn't union an int and a string, because it would lead to a plethora of strange bugs. But the variant type is a way to handle it. And it always has the knowledge about the type that it stores. You can switch the type and it will also know. You can get the type using the... You can get the value from the variant using a concrete type, or the index of the type. And you can write your own visitors for the variant. As you can see here, we have just one struct with a few overloads. And depending on the value that is stored in the variant, the correct overload will get used. This is a good mechanism for writing state machines, for example. And moving your polymorphism more into the static way. Oh, and you can also write you can also visit several variants at once. So if you have, let's say, a box and the value from the box as two different variants, you can have a visitor which matches what's inside and what's on the outside of the box. If the container of this, if the box is of a valid type. So let's say if it's a glass container for fluids or cardboard containers for cats. The next addition is the optional class. And who could tell what this function returns? Do you want to guess? Can you actually tell? Looking at the signature, I wouldn't even know if it's dynamically allocated or not. And I have no idea how it will return an error. If it will throw an exception, if it will allocate an int with a negative value. So how about this one? Is this any better? Who thinks it's better? Okay. So it is a bit better, but still you don't know how it signalizes the errors. And how about this one? Does anyone want to guess how it will return an error? What it will return or throw in case of an error? Will it throw at all? Based on this signature, I would guess that it doesn't throw. It will just return an empty optional. And I think this one is actually much more understandable. So if you are designing interfaces, you should use optional. And if you are designing structs with data, and the parts of the data could be present or not, like a nickname, you can always have it as an optional. And if there is no nickname, you could initialize it using the std nullopt value. And you can also use optional in function parameters. So if you don't have an expiring password, you can just pass an empty optional to this function. And from the signature, we already see that the password could expire or not. Another great addition is the string view class. So probably all of you has, probably many of you had to write a function which took a const char star and a string overload. And yeah, probably the length was known in some cases, the length was unknown in other cases. So this really leads to lots of overloads. And using string view, you can just write one overload. It will be a non-owning overload, so it won't create a copy. It will reuse the data from the string passed, and it will always know its length. So if the length is unknown, it will just calculate it if you don't give it. And I have a question to you. Which one of those could be faster? Who thinks the first one will be faster? Who thinks the second one will be faster? Do you have an idea why?
Copy in the second. The first one, there is I think the string is created from the literal.
Yes, exactly. You have a dynamic allocation hidden in the first example. You pass you pass a C string to a function get which operates on a std string, so it will have to create the std string. And the second one will just create a string view, which is just a pointer and a length, and no dynamic allocations are involved. So you can also use string view for performance. Another addition in the 17 standard was parallel algorithms. So you could use many algorithms, giving them an execution policy. stdsec is the default policy that if you use an algorithm from the older standards, it behaves the same if you give them if you use a parallel equivalent with stdsec. But you can also parallelize using the stdpar policy, or you could allow for vectorization using the par unsec. And you use it like this. You just call the specific algorithm using the policy as the first algorithm argument, and then you pass the other arguments as usual. So those are the standard functions that are allowing for parallelization. To fit them in one slide, I had to use the bash notation, shell notation for multiple strings. You can see that there are almost 70 of those, and also some newer added, like std reduce. And I think this sums up the most important features from C++ 17. So we can now talk a bit about what comes in the future. So for C++ 20, concepts, which is a great feature, was already voted in. And it's a mechanism to write simpler templates and to have more type safety in templates. There are several concepts defined by the standard. Hashable was one of them. It's actually more sophisticated than my example. So you have requires, some requirements for a concept. And then if you use them in a template, the compiler will check for you if you could use them or not. And you could even overload your function based on what concept type do you give it. If it's a forward iterator or a random access iterator, for example. And another benefit are the error messages. So if you declare a list and try to sort it, you will get 50 or more lines of template error bloat. And I guess no one of you wants to read through it. If you use concepts, on the other hand, let's say those are 3 lines, you get just a simple error which already specifies what's not okay with calling sort on a list. So in this case, the iterator type is not okay, but I guess it's pretty clear. Another addition to C++ 20 are contracts. So this way, you could specify the preconditions and postconditions for your function. And also you can define asserts, which aren't debug macros, but actual code. So the tools, the compiler can understand it better. And if you look at the beginning of this function, the signature of this function, you see that the expects clause is specified. It's something that is checked before the execution of the actual body of the function. And also we have an ensures clause, and this is what is being checked after the function returns. In this case, we say that the function will return, that we want to check v2, which is return, and we want to check if it's sorted. And since it's not a lightweight check, we define it as audit and not default. So we have several enforcing levels here. Default is for lightweight checks. Audit is for heavyweight checks, which you can disable if you don't want them. And axiom is for tooling and for formal comments. So you can make a comment, but understandable by the compiler and static analyzers. And if you want to have the most performance, you can even disable the default ones if there's need. Another addition to C++20 are coroutines. So if you know the coroutines from Python, the same came to C++ now. So this small generator will get executed one iteration by another. So if you call it the first time, it will create the current variable, then check the condition of the while, return the current variable, and finish execution for now. If you call it a second time, it will increase the current value by 2, and do another iteration of the loop, returning 2 this time, and so on and so forth. And it allows for great increase in concurrent code, and thus in performance. You also have 2 other keywords, because co-yield is a keyword. So the co-await is another keyword, and co-return is yet another one. So in this case, we have a coroutine that loads the resource, and calling coroutine which could wait or perform some other work while waiting for that resource. Then we have the fetch line, which works the same way, and co-return, which is actually the exit moment of the coroutine. As you can see in the last line, we have unexpected, so it's a way to return errors if, while not using exceptions, if they are too heavyweight. And exceptions will probably be gone from the common use in C++ in a few years. Another addition to C++, probably 20, but it also could be C++ 23. It's not clear now if they will make it in time, are modules. If you are concerned about compiling times of C++, this is the feature that will help you. So if you write a simple include iostream int main std cout hello world, and that's it, the actual source code after pre-processing will be about 500,000 lines long. And I think this is quite too much. So using modules, you could just import a module with, let's say, the whole STL, or even just cout. I'm not sure how they will be packaged. And this will greatly speed the compile times. And it will also help reuse of C++ code, because writing package managers will get much easier. And you also won't have to repeat yourself. If you like the dry principle, you won't need to write the same declaration in the header file and the source file. Another addition are meta classes. So this is an interesting feature to write a class of classes, let's say. Let's say you want to define an interface, like in Java or C#. In C++ for now, you couldn't semantically say it's an interface. You could, and now you will be able to. You can define constraints and for your type of classes, and add to what's defined. So if we write this simple interface shape with a name function, like the below one, what the compiler will do is it will check if our interface doesn't contain any data and give us an error if it does. It will iterate through all the functions in the interface, adding public access rights to the member function, making it pure virtual, like every interface should have, and adding this to this target interface class, or meta class. And also add a virtual destructor, which is now accepted. Oh, and maybe let me add that we will have several meta classes, like for values, for flag enums, if you like to order some flags, or if you need to. You could use a meta class for this, for the whole range of similar flag enums. It could also replace some mechanisms from C++ CLI or Qt. And you could also, of course, define your own meta classes, if this will suit you. For the value meta class, for example, you will have many operators, and it will set the behavior of your meta class, such as it will have value semantics. So it will behave like a usual value. Let's move to ecosystem evolution. We already passed time, so let's do it quickly. So C++ had many problems in the past times, slow compile times. Well, it still has this one. And compiler errors could be sophisticated. Templates are hard to debug. You had leaks. And you didn't really have a central place to go to learn more. And now, much of this has changed. Something with Boost and our libraries. We have a de facto standard generator of builds, which is CMake. We have a de facto standard package manager. Common is becoming one. With the introduction of Clang as a compiler, you now have faster compile times and faster code. As the competency between Clang and GCC moved, GCC also improved in both of those areas. And you can use Clang as a building tool, or LLVM as building tools for other interesting things, like interpreter for C++. There are also sanitizers, which Andrzej already talked about. And there is a feature, a tool to debug templates called MetaShell. You could step through instantiations of templates. And now, since we have isocpp.org and other online resources, CPP reference, for example, and lots of conference videos and conferences, learning about C++ is really much easier and faster. So, a few of the resources. If you know awesome projects on GitHub, those are basically a list of resources for a language, containing recommended classes, recommended libraries, recommended books, recommended videos. And C++ has such a repo, which I recommend to you to see and pick what's interesting for you there. We have isocpp.org. Okay, I think I talked about the rest of those. Do you maybe have any questions? Because I think I'm done. Yes?
How does it compare to Rust?
Okay.
The new additions to C++, because obviously it's evolving, but some of the people actually move to Rust. I mean, I know that they want to rewrite some of the modules in Rust for Firefox, and their grand goal is to write the whole Firefox in Rust. So how does it compare?
So parts of Firefox are already rewritten to Rust.
Yeah.
But I don't think C++ is going anywhere. They are both systems programming languages. But if you look at the comparison of pure performance, it actually turns out that C++ is still a bit faster. So if you care for the absolute performance, I guess C++ is the way to go. But Rust is also an interesting language. and it has its fields.
Okay.
Any other questions? Okay, so thanks for coming.
Oh.